Given a state system of the form here, where the states X are all controllable through U, we can use state feedback to do pole placement. We discussed that earlier. There are three ways that you can do this calculation. One is just to brute force the whole thing out. The other is to brute force it out, but start with A in controller canonical form. And the third way, which we'll discuss here, is to use Ackerman's formula. Ackerman's formula for K is this form here. A is a unit vector of the form here. P is a controllability matrix, and then you'll need to invert it. And phi desired of A is a matrix polynomial where the polynomial is the polynomial of the desired closed loop characteristic equation evaluated at the matrix value A. So it has a form that looks like this. Let's illustrate this by example. Given the second order system in state space form, I want to create a closed loop system where the desired poles are at -2 plus or minus 2i. That would correspond to a settling time of 2 seconds and a damping ratio of 0.707. From the desired poles, I can write down the desired closed loop characteristic equation. Now I'm ready for Ackerman's formula. The controllability matrix is given by this value here. Remember, the system has to be controllable, and by definition, a controllable system has a controllability matrix, which is invertible, which is required for Ackerman's formula. In our case, the system is controllable, and so P, the controllability matrix, is invertible. Next, I'm going to evaluate the desired closed loop characteristic equation with the matrix A. Substituting A into the desired closed loop characteristic equation, I have the matrix equation shown here in green. And after doing the algebra, I have the value here. Now I need to substitute all these values back into Ackerman's form. Completing the algebra, I end up with K is equal to 4.6 and minus 6.5. Let's verify that. So I substitute the U is equal to minus Kx, my state feedback, into the value for U here in the closed loop system using the value of K of 4.6 and minus 6.5. The equation looks like this. The closed loop system has an A value as shown here, and indeed the eigenvalues of A are -2 plus or minus 2i. Now I've cheated here a little bit and I haven't held on to all the significant figures, so if you put this in, you're going to end up with a value that's not exactly the same. So you can use Ackerman's formula to compute the value for K for a state feedback system where U is equal to minus Kx. You don't have to have A in a diagonal form or controller canonical form. It can be in any form you want. The catch is that it does require you to take the inverse of a matrix. The rest of it's just all algebra.